This is basically a continuation of last week where we started considering elastic constants, and we looked at basic stresses and strains, elastic modulus, looked at shear stresses, shear strains, and we mentioned the shear modulus. We looked at Poisson's ratio last week. It was probably a new elastic constant you haven't heard of before. What we're going to do this week is continue with this. So this is going to be extremely dry here. So we're going to talk about the general state of stress and strain here. So we're going to develop more elastic constants essentially. So in practice, metals are what's called polycrystalline and have crystal grains of different properties in different directions. So since the grains are very small and they're normally random orientated, we make an assumption about our metallic materials, and that assumption is that for metallic materials as a whole, they're classified as homogeneous and isotropic. Okay, so you may not have heard those terms before, but implicitly in all calculations that we undertake with metallic materials, steels, alumina alloys, coppers, whatever, so we're going to define those terms here. So the first one, homogeneous. Homogeneous materials have identical elastic properties at all locations. Isotropic materials, they have identical elastic properties in all directions. So they're different characteristics here, but we will assume our materials are homogeneous and isotropic and have both of those characteristics. I'm going to try and illustrate this here with the diagrams. So if we consider homogeneous materials first of all. So these are material properties that are the same throughout the component. Okay, so imagine this is a piece of bar we're looking at here. And I've got two locations in the component. I've called one location A here, one location B over here. Okay, two different positions in the bar. What homogeneous means is that if we consider I'm just using elastic modulus here as an illustration. This relates to all elastic constants, whether we're talking about Poisson's ratio or rigidity modulus. What homogeneous means, at point A, we have three directions, the X, Y, and Z, and it's showing that the elastic modulus is different in the three directions. So we have a large elastic modulus in the X, we have a slightly smaller elastic modulus in the Y, and a smaller elastic modulus in the Z. What homogeneous means is that the material properties are consistent throughout the structure. So in other words, if I go to B over here, you can clearly see that if I take the E in the X direction, at point B, that's the same E in the X direction. It's got the same magnitude, same value. If I consider, say, in the Y direction at point A, my E in the Y at A is the same as E in the Y at B. Z direction, point A, there's my E in the Z, and that will be the same E in the Z at point B. So at every point I take in my piece of bar here, I will have the same X, Y, and Z elastic modulus or Young's modulus values, but they're actually different in the three different directions. So that's what homogeneous means. If I try and describe now isotropic materials, they have the same material properties in all directions. So now if we take point A again, B up here, we've got 2 points in the structure, you can see that at point A, the material elastic modulus, or the Young's modulus, it's the same now in all the directions. I've got E1, and E1 in the X, Y, and Z directions. They're all the same. But if I go to point B up here, again, they're the same in all directions, but they're actually different to what they were at A. So now I have the E2s in the X, Y, and Z direction. So isotropic means at a particular point in the structure, point A, material properties, the elastic modulus in this case, is the same in all directions. If I go to point B, again I've got elastic modulus same in all directions, but it's a different elastic modulus to what I had at point A. So that's isotropic. So what we try and do is put those two together. So we always assume that our metallic materials are homogeneous and isotropic. So in other words, what we're now saying, if we go to our points in our structure now, at point A, here, considering the Young's modulus. The E is the same in all directions, so that's kind of isotropic in its definition. But if I now go to point B, I find the E's are the same, again, in all directions. So that now makes it homogeneous, because any point in the structure I'm getting the same properties, and isotropic because any point in the structure I consider I'm getting the same properties in all directions. So that's what homogeneous and isotropic means, and that's something we assume for all metallic materials. Just going to show you this. I'm going to illustrate this. In practice, it's not quite right. It's a reasonable assumption, as you'll see in a moment. What I'm showing you here is a piece of plate that's being rolled, and it has three salient directions here. The L direction, the length direction it's termed here, that's the longitudinal direction of a piece of plate, and that's a direction in which I'm considering it rolled in here, but it could be extruded, it could be forged in that direction. That's its main processing direction. We can have other directions. I've got the T direction here, which relates to the width. T is the width of the plate here, sometimes called the long transverse direction of the plate. And then we've also got the S, which is the thickness or the short transverse direction of the plate, shown here, this S value, the thickness of the plate. So there's our three directions. Now, if you look at material properties associated with those directions, and this is just an extract here from an industrial reference manual for materials. It's actually an American reference manual, so all the properties here are actually in thousands of pounds per square inch. They're actually all in KSI, as the units show there. But I'm not bothered about the actual values. I just want to show you the characteristics here. If you want to convert them into newtons per meter squared, then the conversion 10 KSI is approximately equal to 70 newtons per millimeter squared if you want to do the conversions. But I'm just looking at the characteristics here. And what we've got is a particular type of plate here. This is actually a steel plate, I think. It's got its temper. And we've got different thicknesses of the plate. I'm not really bothered about that, but that's just the way the information's been supplied. So it's thicknesses, again, they'll be in inches because it's an American standard. So it's 1/4 of an inch to 1.5 inch, and 1.5 inch to 2 inches, and so on. Different thicknesses. The A and the B in this particular table relate to statistical properties, statistical values. So it's to do with confidence levels. We don't need to worry about that. All I'm interested in is this first column, is A column, if you like, here. And what it's trying to show us is the various strength properties associated with a piece of material, a piece of steel here. Now, again, because it's an American document, they've used slightly different symbols. They've got FTU. That would mean actually the ultimate tensile strength to us. If you read the column here, what it's showing you is for the longitudinal direction of our plate, going back to this diagram. So for this direction, it's given us a value of 70 thousands of pounds per square inch. If we look at the LT direction, again, that would be the LT direction, would be this direction of the plate. They've given us a value of 71 KSI in this case. And if you look at the ST direction, which is the thickness, they've given us 66 KSI. So I'm not bothered about the actual specific values there. But I'm just trying to show you that we would assume, if they're isotropic and homogeneous, that the values in all three of those directions would be the same. So the assumption is not unreasonable. Certainly between the longitudinal and long transverse, it's fairly good. If we said it was 70 KSI, then that would be quite reasonable for both of those. It's slightly different in the short transverse, slightly less in the short transverse. But generally speaking, you can see that they're very similar properties. If we consider the yield, they've got two yields here. They've got one in tension and one in compression. This is the yield, so they've called it FTY here. That would be our yield stress in tension using the Greek symbol there, sigma. And again, you can see in the L direction, 59, in the LT direction, 60, ST is dropped again to 54. But between the L and the LT direction, which is the direction you would predominantly design your component in, again, the properties are very, very similar. They have also given here properties for compression. They call it FCY here. That's a compressive stress. And again, you can see that the properties in compression are very similar. For the longitudinal direction, they get 58. For the LT direction, 61. The ST direction this time is 62. Okay. So you can see from that that the assumption of isotropic homogeneous is reasonable. And it's really only time I've seen people really concerned about these different properties and directions is in the aerospace industry. When you're designing components to the nth degree, you may be a bit more cautious about what values you use. But nevertheless, you still assume the isotropic homogeneous principle. Something else to notice there, the tension and compression values. Notice how they're very similar for the yield, because we don't actually test in compression often. We use a tensile test, and we often assume that the compression values are very similar to the tension values. And you can see that that's again a reasonable assumption. My sort of my tension yield stresses are around about sort of 60ish there, and again you can say same for compression. It's a reasonable assumption to assume that the compression yield strength is very similar to the tension yield strengths. Again, it's another little extract here. Again, it's showing a different material. It can still, I think it's steel again. We're considering here, sheet strip steel here. And again, I was just showing you one column. But again, you can see for the ultimate tensile strengths in the L and the LT direction, very similar here. Much stronger material we're talking about here. And again, for the yield strengths here, again, very similar. Okay, so I think that kind of illustrates that the isotropic homogeneous is reasonable. And I've just shown you the diagram here. On the right hand side, we normally test in terms of tension. So this would be our typical tension test, would be this line here up to the yield point and then onto the ultimate failure point there. In compression, we often assume that diagram is replicated, but obviously we've got compressive stresses and compressive strains here. But it's an assumption we make that in compression we get the same kind of diagram. So the elastic modulus, if you like, compressors assume the same. And the yield strength is often termed to be the same. And you can see it's not unreasonable. It's actually stronger here. The yield strength here is actually stronger in this particular case than it is in the tension. So it's not an unreasonable assumption. You have to be careful trying to assume the ultimate strength, though, because when you're compressing something, in some cases it can actually fail, although it's in compression, it actually fail in tension because it has secondary tension forces in some sort of specimen. So the ultimate compression strength is a bit more difficult to define. And of course, a member subject to compression can actually fail in buckling, which is a separate mode of failure to that of yielding. But certainly the yield strength in compression is often assumed to be the same as the yield strength in tension. And as you can see from that diagram, that would not be an unreasonable assumption there. And this is just a couple of examples from industry to show how engineers do account for this. This is a attachment bracket for a particular component on an aircraft engine, I think it was, and the most highly stressed flange, which is this top flange here, was designed with the L and the LT directions. This flange here is taking a significant load compared to the lower flange here. So the engineers designed this so that the L and the LT direction, which are the stronger directions for the material property, are sort of withstanding the highest stresses, the highest loads that have been applied on this top flange. So engineers do think about this kind of orientation of the direction of the processing of materials because it does affect the strengths, and so they will consider this in their designs, particularly when you're looking at designs that are really high stress, like in the aerospace industry. Where you're really working materials to their maximum, you do account for these directions, even though we're assuming isotropic homogeneous throughout our calculations. So when you see typical material properties, these are just typical values. Let's put here, I've got commercial steels, a whole range of commercial steels. We're interested in values such as the yield or the proof strengths, the ultimate tensile strengths, that's when it's actually broken into bits, and the Young's modulus or the elastic modulus. We're interested in those primarily. Those are very important aspects of our stress strain diagram. And we're assuming here that the yield strengths, if you take this particular standard structural steel here, the yield strength is the same in all directions, in all locations in the material, and it's the same for the ultimate tensile strength, same for the elastic modulus. We're assuming those properties are typical throughout the component or the piece of bar, whatever we're considering. Okay, so when you see material properties, for metallic materials, they assume isotropic and homogeneous. Let's review the general state of stress and strain. Let's consider the deformable body that's shown in figure 8. which is under a system of loads, and we're going to isolate an elemental cube of material surrounding point O in the figure. So here's point O, and here's the elemental cube we're extracting from the deformable body. We can assume this body is essentially a component in a structure, for example a structural member in an electricity pylon, or a structural member within an aircraft wing, etc. And this elemental cube has been extracted from this component, or from this material. Now the elemental cube will have various forces acting on each of the faces, such that it's held in a state of equilibrium within the body. So we're assuming the entire deformable body is in equilibrium, the actual structural member, and so within that structural member a very, very small element of the material is also in equilibrium. By equilibrium we mean it's not moving left or right, up or down, and it's not rotating. So the forces applied to the elemental cube can be represented by resultant forces labelled F1, F2 and F3, shown in figure 7. Here's resultant force F1, resultant force F2 and F3, and there'll be equal and opposite forces on the hidden sides of the cube. What can often be done is the resultant forces F1, F2 and F3 at their oblique angles to the individual surfaces can actually be resolved into mutual orthogonal forces in the X, the Y and the Z direction, as shown in figure 9 here. And we'll consider the effects of resolution into the X, Y and Z directions on the next slide. Continue with our general state. If the resultant forces from the previous slide, that's F1, F2 and F3, are resolved into the 3 coordinate directions shown in figure 9 and also in figure 10 here, X, Y and Z directions, so we resolve our forces into the X, Y and Z axis system. We then divide these Fx, Fy and Fz forces by the area of the face of the cube of the general state. A 3-dimensional stress system is formed, as shown in figure 10 here. So in figure 10 here we have our direct stress, sigma x. That's determined by the force in the x direction divided by the cross-sectional area of the x face. And similarly, we can determine the direct stress in the y direction and the direct stress in the z direction. Notice on the x, y and z face, we've also added 2 shear stresses. So we have a shear stress on the x face in the y direction, and we have a shear stress on the x face in the z direction. And equally, we have 2 shear stresses labelled on the y face and 2 shear stresses labelled on the x face. Again, we will have equal and opposite stresses on the hidden faces. So in figure 10 it appears we have 3 direct stresses to consider in our general state and 6 shear stresses. So we're going to consider the principle of complementary shear stresses here. So it looks like on the previous diagram we had 9 stress components, as I said before. We had 3 direct stresses and 6 shear stresses. What we're going to do is show how we can eliminate some of the shear stresses and reduce the quantity of them. So what I'm considering here in figure 11 is a view on the Z face of the cube. So in the previous diagram it's 3-dimensional. I'm just looking on the Z face here, that's all, for this particular exercise. And if I look on the Z face, this is what I see. I see the X stress component, obviously is on either side of the cube here, and I see my Y component, direct stress in the Y, shown there on the face, looking on the Z face. And then I see these shear components here. So I've got my shear components. So the shear XY, shear YX there, shear YX on the bottom, shear XY over here. Okay, so that's looking at on a sort of 2-dimensional view on the Z face. That's what I see. So I'm seeing these 6 stresses effectively. Now, if you consider equilibrium, this is the basic concept on which we undertake all our stress analysis. The summation of all the forces on an object, on that section shown there, so summation of all the forces in the x direction must equal to 0, the summation of all the forces in the y direction and the summation of all the moments about any point must equal to 0. That's the basis on which we undertake all our analysis. That's what we've always used. So just by looking at the what's called translational equilibrium, that's the vertical and horizontal equilibrium, I think it's fairly clear to see that the stresses, the shear stress in the vertical sense here, there's tau xy and the tau xy, they have to be the same. They're in equal and opposite directions, but on the right-hand side of the face, the shear stress is going up the page. On the left-hand side of the face, the shear stress is going down the page. They've got the same magnitude, they have different directions, and that puts it in what's called vertical equilibrium. The upward force is equal to the downward force, in other words. And the same with the horizontal. In the horizontal direction, on the top of the surface, we've got the tau yx going from left to right, and that has to be balanced in the horizontal direction by tau yx going from right to left. Okay, same magnitude but opposite direction. So that's not unreasonable. If we want to keep it in horizontal equilibrium, the forces to the left must equal the forces to the right. Let's consider the rotational equilibrium, slightly more complicated here. Again, we're still considering this complementary shear stress principle. What we're going to do here is take moments about the corner, point L. I've highlighted it with the blue dot down below. And we're going to assume clockwise moments are positive for this analysis. Now we're talking about a cube here. It's a very, very small elemental cube, and the lengths of each of the sides of the cube, the lengths across here, the lengths here, they're all lengths of L I'm using. Okay, so what I'm going to do is take the moments about point, the bottom left-hand point here, point O. So if you consider the top force, or the top shear stress, the tau yx here, if I want to work out what the force is on that top surface, so I'm trying to find the actual force now on that top surface going in this direction. To find the force, you have to multiply the stress, shear stress, by the area over which it acts. So that shear stress is this shear stress here. That's acting on the entire area on the top of the cube in this direction. So to find the force associated with that stress, it would be the shear stress multiplied by L squared, because don't forget each of these sides are dimension L. We're talking about a cube here, considering a cube here, so each side is L. So the area is L squared, so the stress multiplied by the area will give us the force. So the force it's acting, if I call it F there, on that top surface. And the distance we are away from the corner we're considering to rotate about, the bottom left-hand corner, is height L. Don't forget each of these dimensions are L, so that's distance L away from the corner. So the moment, the clockwise moment, F, the tau xy, multiplied by the L squared, and then multiplied by the height of the block from our corner we're considering, then that will be dimension L. So that gives us a moment, a clockwise moment of the force times the distance. Anti-clockwise moment is generated by this force over here. So in this direction, we will have another force, and that force will be the tau xy multiplied by the area. The area is here, the L times the L. But that force times distance L, because this is distance L here, will be going in an anti-clockwise direction. So about point O, this force, call it F here, multiplied by L is going in an anti-clockwise sense, whereas this force multiplied by L is going in a clockwise sense. Another moment supplied, they must equal to 0. So you can see clearly that all the L terms cancel. If I divide throughout by L cubed, then all the L terms cancel, rearranging the equation. The stress Yx, shown here on the top, must then equal the stress Xy on the side. So in other words, those two stresses have to be the same. I've labelled them as different in my initial considerations, but actually for equilibrium they have to be the same. Otherwise I won't get moment equilibrium for my little cube here. So what that boils down to, as far as we're concerned, is that although we considered initially there were 6 shear stresses to consider, there's actually only ever going to be 3 shear stresses. So when we come to analyse our 3-dimensional structures, there are only 6 independent stress components to consider to define the state of stress at a point. There'll be the 3 direct stresses, the sigma x, sigma y, and sigma z, and there'll be 3 shear stresses associated, not 6 we originally assumed. So that's just a backdrop to try and show you how we consider these 6 components in a stress analysis. Let's now consider generalized Hooke's law. In last week's lecture we considered Hooke's law, which of course relates to the linear proportion of a stress-strain diagram in a uniaxial stress situation. Here we're going to consider the direct strains that are due to a general triaxial, that's a 3-dimensional stress system, is shown in figure 13 below. Note in the figure shear stresses have been omitted to aid simplification, so only the normal stresses, or the normal strains, will be considered. So on the left-hand side of figure 13 we have our triaxial stress system with our 3 direct stresses applied, and this is now broken down into the 3 mutually orthogonal directions of x, y and z. So for the left-hand diagram we have a stress x applied in the x direction, we have a stress y applied in the vertical sense, and we have this stress z applied in this direction, shown here. What we're going to do now is consider the various normal strains that are induced by applying the triaxial stress situation. So if I take my 3 stresses again, I'm going to just highlight them here again. So strain in the x direction, shown here, is due to the stress in the x direction. Okay, stress divided by E is strain, so my strain in direction here is a positive. When I pull in the direction of the arrow here, the strain in that direction is positive. Okay, so positive strain due to the positive stress applied here. If I consider though the y stress here, shown here, I've got y stress shown top and bottom of my cube here. That y stress, if I apply that stress to the cube, that will elongate the cube in the y direction, so it will have a positive strain in the y direction. But going back to last week's work on Poisson's ratio, that will actually produce a negative strain in the x direction because of the Poisson effect. It will get thinner in the x direction, because it's getting longer in the y direction. So we'll actually have a negative strain in the x direction from the stress in the y direction. So that's why I've got a negative on my strain in the x direction from the stress in the y direction. And similarly, if I consider the stress in the z direction here, there's my stress or my force, you want to think of it as pulling in that direction, so I get stress in that direction. So if I just think of that applied to my cube here, that will elongate the cube in the z direction, so I have a positive strain in the z, but it will contract in the x and the y direction, but I'm considering the x direction here, it will contract in the x direction. So again, in the x direction, I'm actually going to get a negative strain from the positive z strain I've got applied here, the positive z stress is applied. And this is trying to illustrate how Hooke's law works here. We're going to have sort of 3 dimensions here, and strains in all dimensions, the x, y, and z dimensions, and they affect the overall strain in the x, the y, and the z. So for example, if I just pulled it in the x direction, I would have a strain in the x direction which is positive, but if I'm going to pull it in the y direction and the z direction, I'm going to actually reduce the strain in the x direction, because when I pull in the y and the z directions, I get negative strains in the x direction from the Poisson effect. So it complicates our system. This is where we consider triaxial stress systems. Our generalized Hooke's law equations are shown here for the 3 different directions. So in the first one, I'm going to consider strain in the x direction. Strain, don't forget, is the epsilon symbol we used. So to calculate the strain in the x direction, we would have the stress in the x direction divided by the elastic modulus. That's the basic definition of strain. Don't forget, E is equal to stress over strain. If you go back to last week's work, uniaxial situation as stress divided by strain. What we're considering here is a triaxial situation. so stress in 3 directions. So that would be my strain in the x direction. It'd be stress x divided by E. But if I'm going to now consider the strain in the x direction, I've got to now consider the effect of the y strain on the x direction. So pulling in the y direction, stressing my component in the y direction will produce a negative strain in the x direction due to the Possion effect. So the stress y over the E there is a strain in the y direction when I'm pulling in the y, but in the x direction, which is the strain I'm considering here, I will have the Possion effect to consider, and that will be negative. Don't forget the Possion formula has a negative value in it. So that will be a negative strain in the x direction. And similarly, if I consider stress in the z direction, the strain in the z direction will be positive, but in the x direction, the Possion effect of that strain would be negative. To work out my total strain in the x direction for a triaxial situation, it's not just calculating the strain in the x direction from the stress in the x direction. I have to consider the Possion effects of the strain in the y direction and the strain in the z direction. So that gives us what's called generalized Hooke's law for calculating the strain in the x direction. All I've done here is just factorize because the elastic modulus is common, because we're assuming isotropic and homogeneous materials, then the elastic modulus is common. I've just factorized on the E, on the right-hand side equation. Same equation, just factorized. I've also factorized on the 2 mu terms here, where I've got my Poisson's ratio. Again, I've factorized on those. So it's just a factorized form on the right-hand side. I tendency to use the left-hand equation in my calculation. I think it's more explicit to what we're actually doing. But the right-hand equation is just a factorized form. Less number crunching there. Now, the same kind of process applies if we consider strain in the y direction from above. We're now considering the strain in the y, okay, so that would be the stress in the y over the E, but now we've got to consider the Possion effects of the stress in the x over the E, so that's a negative effect there, and also the effect of the strain in the z, Possion effect there, okay. So the strain in the y would be the stress in the y upon E minus the Possion effects of the other strains there. And again, I factorized on the right hand side. And then finally, if we look at the strain in the z direction, that will be the stress in the z over the E, but we've got to then take from that the stress in the x over the E, or the strain in the x multiplied by the Possion effect, and we've also got to subtract from that the Possion effect and strain in the y direction. Okay. So 3 different equations, they're all doing similar kind of things, but in different directions, x, y, and z. So more complicated when we're thinking about 3-dimensional stresses, 3-dimensional strains in this case. Okay, so the equation on the previous slide, equation 8, they represent generalized Hooke's law. So for a body acted on by a general 3D stress system, the strain in any direction is that due to the stress acting in that direction, plus the superimposed strains resulting from the Possion effect of the stresses that are active in the other 2 coordinate directions. So that's what it's showing on the previous diagram. Okay. And of course, remember, these equations only apply to homogeneous isotropic materials where the stresses are within the elastic region of the stress-strain curve. I'm just showing you here biaxial stress situation. It's slightly condensed form, no z stress. So strain in the x direction will be the stress in the x divided by E, and then we will take from that the Possion effect of the stress in the y divided by the E. Okay, again factorise on the right hand side. If we consider strain in the y, that will be stress in the y divided by the E, and we will subtract from that the Possion effect of the stress in the x divided by E. But if you consider the z direction, there will be a strain in the z here. Of course, there's no stress applied in the z, but there will be a strain in the z because of the Possion effect of the other 2 directions. So here you don't see a stress z upon E because it's a biaxial situation. There's no stress z applied, but you will see the Possion effect of the strain in the x upon E, shown here, and you will see the Possion effect of the stress in the y upon E, which is shown here. So you do get a strain in the Z, even though there's no stress in the Z, because it's based on the Possion effect of the strain in the X and the strain in the Y. So again, be careful of a biaxial situation. If it asks you for all three strains, don't just think there's a strain in the X and the Y, because that's where the stresses are applied. There will be a strain induced in the Z. It will be due to the Possion effect of the other two strains. And again, we'll look at that in the examples. So if we now rearrange equations 9a and 9b from the previous slide, which were in terms of finding strains, we can actually derive stresses from the strains. And these are the rearranged equations. So to find stress in the x direction, given the strain in the x direction and the strain in the y direction, and also to find the stress in the y direction, given the strain in the y direction and the strain in the x direction. So equations 10a and 10b shown above are the experimental stress analysis form of the generalized Hooke's law for a biaxial state of stress. In other words, as stresses cannot be measured directly, engineers measure strains and then deduce the stresses from the equations shown above. So in practice, we can't actually measure a stress in the x and y direction, but we can measure a change in length in the x or the y direction, and from that we can find the strain in that direction, and then from the above equations we can find the stresses in the particular directions. The proof of equations 10a and 10b from equations 9a and 9b is shown on the following slide for your reference. Here is the proof using equations 9a and 9b to derive equation 10a. It's a very similar approach to find equation 10b. I'll let you review the proof at your own pace. So exercise 7. We've got a thin skin panel here. It's actually a 2024T3 if you want the actual material specification used for aircraft fuselage skin panels. So it's aluminium alloy and it's subject to biaxial stresses. So biaxial stress shown. So we've got 160 meganewtons per meter squared, let's just say in the x direction, and it's 80 meganewtons per meter squared in the y direction. Okay, so it's biaxial, nothing in the z direction. So we're asking the question to use generalized Hooke's law to calculate the change in the length and the breadth of this panel. We're told to assume that the Young's modulus is 69 giganewtons per meter squared and the Poisson's ratio is 0.33. We're given some geometry here. We've got the dimensions. It's 400 millimeters length and 150 millimeters wide. So let's have a look at this, see if we can analyze this together. I'm going to find a strain in the x direction first of all, so step 1 if you like. So strain in the x direction, we expect it will be the stress in the x direction divided by the E, elastic modulus, minus now the Poisson effect of the stress in the y direction, and that's divided by E also. So that would be our first equation. This would be stress in the x direction, shown here. This would be stress in the y direction, and we've got the elastic modulus given in the question. So we're going to find the strain in the x direction. I'm going to let you find the strain in the x direction. You've got stresses, you've got the E's, got all the values you need there, Poisson's ratio and so on. And I'll give you my value. You can check the values out. So 1936 microstrain I'm using here. And it will also want us to find a change in length in the x direction. Well, we know that the strain in the x direction is equal to the change in length, I'll call that delta x, over the original length, so I call that L in the x. So simply transposing that equation, we can find the change in the x direction. It's going to be the strain in the x direction. That's multiplied by the length in the x direction. Again, I'll give you my values. Don't forget this will be length in the x direction. This will be length in the y direction. Okay, I'll give you my values in the sheet. So 0.774 I get here, which is what it says on the sheet there. So do you want to have a go at putting the numbers into the equation? Millimeters here I'm using. And to do the strain in the y and the change in lengths in the y, it's almost exactly the same. It's just that the equations will be slightly different. You can see the beauty of using isotropic homogeneous here, because the E's might be slightly different. If you go back to our tables we looked at on the previous slides, they were slightly different in the X and the Y directions, in the L and the T directions, but they're only just slightly different. So it kind of saves us having to do these sort of using different values in the two different directions if we assume isotropic homogeneous. In this case, the E is the same throughout. So 394.2 microstrain. Find the change in length in X and Y direction. I'll just put the formula down. That would just be simply delta in the Y is equal to the strain calculated in the Y multiplied by the N in the Y. According to my answer, I get 0.059 millimeters. Here's the full worked solution for exercise 7. Your strain in the X direction calculated here, and the change in length delta X calculated here, and the strain in the Y direction calculated here, and the change in length in the Y direction shown here. Exercise 7 didn't want us to calculate the strain in the Z direction, but for reference I've shown the calculation here. So strain in the Z direction for this biaxial stress situation, notice there was no stress Z applied, just stress in the X and the Y directions. So strain in the Z is equal to the negative Possion effect of the strain in the X direction, and we take away from that the Possion effect of the strain in the Y direction. And this allows us to factorize the equation, so they're both terms are negative, and nu and E are common to both terms, so I've got my stress X and stress Y in the bracket. Then inserting my values for the nu, for the E, and for the stress X and the stress Y, I calculate the strain in the Z direction to be negative 1148 microstrain. So this calculation shows that for a biaxial situation where we have a stress X and a stress Y applied but no stress Z applied, we still have a strain in the Z direction. And that's due to the Possion effect of the strains in the X and the Y directions. This is now volumetric strain. Volumetric strain, or changes in volume. So as dimensions of the material change during loading, so the volume must also change. So for the rectangular section shown below, which is considered to be again a small element that's removed from a component or a piece of bar, we're assuming it's isotropic here again, so the same material properties in all directions, and it's subject to three principal tension stresses shown. So we've got a stress in the X, the stress in the Y, and the stress in the Z. They're called principal stresses, tension stresses in this case, all right? What we're going to do is derive a little formula here, and mathematically speaking, this is actually quite easy to follow. It's a bit time consuming, but it's fairly easy to follow here. So the original dimensions are X, Y, and Z on our little diagram here. We're going to apply load into these, and we're going to change the dimensions in the X, Y, and Z. So I've called these sort of delta X is going to be the change in the X dimension, a very small change in this X dimension. So change in that dimension there. Delta Y will be a very small change in the Y dimension, okay, and then delta Z, that'll be a very small change in the Z dimension. So these are very, very small changes. So the original volume is X multiplied by the Y multiplied by the Z, and if I want to find the final volume, then I would have in the first bracket out X added to the change in X. So we start off with X, add delta X to it, so that's the new dimension in the X direction when we apply our load into it. In the Y direction here, the change in length is the delta Y, so add in delta y to y gives us now the new dimension in the y sense, and the same with the z. The change in length in the z is a delta z, so adding that to z, that gives us a new length in the z direction. So we could work out the final volume of the object by literally multiplying those three brackets together. If we want to find the change in volume, which often is what we're looking for, the change in volume, I've called it delta V here, then it would be the three brackets again multiplied together for the three different dimensions now that we have because of the applied loading, and we would take from that the original volume, which we've calculated up here. That would be the algebraic equation finding the change in volume, delta V. If I want to find the volumetric strain of the component, so volumetric strain is defined as the change in the volume, my delta V above, divided by the original volume, capital V, then the change in volume would be now this expression here, quite a lengthy expression. The rest of this is sort of basic mathematics, so a bit chunky mathematics here. What we've got to do, it takes a while to do this. I'm not going to do this with you in any great detail, but what we've got on the next line is we're multiplying out the brackets. So don't forget these are binomial brackets, so you would have to sort of multiply these two together, simplify those, and you'd multiply the simplification of that with this bracket. So we'd be expanding brackets for a few minutes here to get this expression shown here. So this line here is the expansion of this line here. That's all it is, just algebraic expansion. We could do that, but it would take us a few minutes to do that, and we'd probably make a few mistakes along the way. So I've done it for us, okay? So that's all we've got, expanding the brackets out. So at the moment, that's quite a substantial formula to calculate the volumetric strain. So, engineers being engineers, we make simplifications, we make assumptions, just like we have about the isotropic homogeneous materials. That makes an assumption. We can make an assumption here about the strains that are called second order strains. The assumption we make is that these sort of strains are very, very small. So the second order terms in our strain equation can be ignored. And what I mean by second order terms are these kind of terms, where you've got a delta multiplied by a delta. So the delta y multiplied by delta z, that would be a second order term. You're multiplying a very small value by a very small value, so you're an even smaller value. So that is considered to be negligible compared to the rest of the calculations. So the same with this one here. I've got delta y multiplied by delta z. This one here, x multiplied by delta z, and this one here especially, I've got three deltas multiplied together. So we would assume that as the deltas are very small values, the products of delta values are going to be even smaller and not really worth considering. So that's the assumption that's made in the analysis that we perform, and that's how we end up with this top line here. This top line here is the assumption that the other terms can be ignored. When you look at this sort of line compared to that, it's a nice simplification. I should also say, of course, that this term here, this first term xyz here, will cancel with the xyz at the back, so that term disappears as well. So a nice simplification we get on the top line there. If we now consider the fraction effect here, we've got on the top xz delta y plus yz delta x plus xy delta z, and it's all divided by xyz. There's actually some cancelling that occurs here. We can actually cancel off some of the terms, you will see. So taking that first term here of xz delta y, we can cancel the x on the top with the x on the bottom, and we can cancel the z on the top with the z on the bottom to leave us with delta y upon y. So that's where that first term comes from. It's basically that divided by that, and it simplifies to this. Okay, that's where the term comes from. And you're the same with all the terms. You can take the next term, the yz delta x, you can divide it by the xyz. You'll see now that the y and the z cancel, so you end up with delta x upon x. And the same with the last term, goes through the motions there, you'll find you end up with delta z upon z. And what you now end up with is simply the volumetric strain is going to be the strain in the y direction. So the change in lengths in the y over the original lengths in the y, that's strain in the y direction. You've got the change in lengths in the x direction divided by the x. That's strain in the x direction. Change in the z divided by the z, that's strain in the z. And that's what you're seeing down here. There's my strain in the z. There's my strain in the y. There's my strain in the x. So therefore the volumetric strain equals the sum of the principal linear strains. So we can see that by making the assumption that the strains are very small and the second order strains can be ignored, we end up with a very simple equation for calculating volumetric strain. Again, looks pretty heavy here, some of the arithmetic here. I'm not going to labour this with you because of time here. But what we're doing here is substituting in equations 8a, 8b and 8c from our previous slide. We're putting them into equation 11. For reference, here's equation 8a, equation 8b, equation 8c. And here are the three equations inserted into the volumetric strain equation. And we'll end up with a simplified equation, so simplifying volumetric strains now, but in terms of stresses. Okay, so this was volumetric strain in terms of strains, and this is another expression of volumetric strain, but in terms of stresses, the x, y and z stress here in the Posson's ratio. It's another equation for working out volumetric strain. Okay, so it's just another variation, but the stresses are involved here. And if you do have a uniaxial situation, just a pure single load or stress applied, that's what a uniaxial stress situation is. So your stress x will not be 0, but your stress y and your stress z will be 0. So for a uniaxial stress situation, the volumetric strain simplifies to this expression here shown in equation 12a. Okay, so again, different problems can involve different equations. There's no point in using equation 12 in a uniaxial stress situation. You can use 12a, the slight simplification of it. Okay, so that's volumetric strain defined for us there. Let's have a look at exercise 8, which is all about volumetric strain. See what we can do with this one. Exercise 8, calculate the volumetric strain in a 10mm diameter steel bar. It's subject to a tensile force of 25 kilonewtons. We're given the length of the bar, 750mm here, and we're given the E and the nu values, 25 kilonewtons per millimeter squared and 0.3 respectively. Okay, I think I'll work everything through in millimeters here because my E is given in millimeters squared here, so I'll work in millimeters. Now this is actually a uniaxial stress situation because we've just got one load applied, so we one stress induced in the bar. So let's take your face from the question as always. A little diagram here. So, and we're given the E value right over here and the Poisson's ratio. Okay, so that's the information out of the question. We've got to try and find the volumetric strain. So we're trying to find the epsilon V known here. So what I think I'll do is I'll work out my strain in the x direction, and I'm going to work out strain in the other directions, the y and the z direction, using the Poisson effect, and I'll add my three strains up. So first of all, let's calculate the tensile stress induced. So stress, I'll call it in the x direction. That will be the force, in this case, divided by the area. Obviously it's a circular section here, so you need to work out the cross-sectional area. I'll give you the values and you can do the number crunching. Direct strain. So my direct strain. Just outline my solution there, alright? So we found the tensile stress, only one stress to find in this case because it's a uniaxial stress situation. We can find the direct strain there. In this case, the lateral strains are due to the Poisson effect. Okay, that'll be sort of x, y and z. So the x is longitudinal, y and z are these lateral strains or diametrical strains, in this case strains in diameter. So they're due to the Poisson effect occurring in this case. So, alright, typical kind of question we will do. So you can see it can get quite thought-provoking when you're thinking about 3 dimensions as to what's happening with the strains. It's the full solution. This is another elastic concept. I won't labour this too much now. Something called a bulk modulus of elasticity. This is a property that sometimes crops up in some questions when you've got components that are subject to compression. So bulk modulus relates to the degree of compressibility of a substance. This property is required when you consider bodies that are immersed in fluid or a fluid subjected to an external pressure. Those are 2 instances where you will consider the bulk modulus effect. So if a hydrostatic pressure, I've called it P here, that means hydrostatic means the same in all directions, acts on a body of volume V, causes a reduction in the volume, delta V, then the bulk modulus, and that's usually given symbol K in most textbooks, is defined as the ratio between the fluid pressure, P, and the volumetric strain, the Epsilon V. So bulk modulus in most textbooks, showing that symbol K, is equal to the negative P, negative because their pressures are applied to the surface, you're compressing it, divided by the volumetric strain, basically a change in volume over the volume. So negative P divided by the volumetric strain is the bulk modulus, okay? And the negative sign there accounts for the reduction in volume. We've always got a reduction in volume here because it's being compressed in all directions. So bulk modulus is another property we consider. If you take this cube again, we've got with our hydrostatic pressure applied, same pressure in all directions here. The principal stresses in all directions are basically the negative pressure values. Whatever the pressure is applied, then the stresses, three direct stresses, will be negative in that direction. So that's what's called a triaxial stress situation again, but all the stresses are equal in this particular situation. And from generalized Hooke's law, we derived earlier, the linear strain in one direction, we use epsilon x in this case, is our stress 1 upon E above minus the Possion effect of the stress 2 upon E minus the Possion effect of the stress 3 upon E. But in this case, the stress 1 is negative P, the stress 2 is negative P, and the stress 3 is negative P. So that simplifies to negative P upon E multiplied by, in brackets, 1 minus 2 nu. Just a factorization of the numerator because negative P is common to all terms. Now if we consider the volumetric strain, epsilon V, we know from previous works that's simply the strain in the X, add the strain in the Y, add the strain in the Z, the three mutually orthogonal strains. In this case, the epsilon X, epsilon Y, and epsilon Z will be the same because we've got the same pressure applied on all surfaces of our cube. Therefore we simply multiply the above equation for epsilon X by 3, shown here. We also note from our previous derivation that the bulk modulus K is negative P divided by the volumetric strain. So hence we have another expression for bulk modulus now. Bulk modulus K can be written as E divided by 3 multiplied by 1 minus 2 nu in brackets, and that's formed by combining the two equations for epsilon V and K shown here and rearranging to make K the subject. So equation 14, another equation for bulk modulus. And again, this equation 14 repeated, we can rearrange the equation, rearranged here to find the elastic modulus multiplied throughout by the denominator here. So another equation 15 just rearranged. Let's look at the relationship between shear stress and shear strain. So to undertake a shear stress test in shear, it's actually quite difficult to do that. And often we use torsion tests to obtain a shear stress strain diagram. So when it says undertaking direct shear, it's not something we normally do. It's normally in a torsion test. And if we plot the values from this torsion test, so we're plotting in this case the shear stress on the vertical axis, against the shear strain, gamma, shear strain on the horizontal axis, we get the shear stress strain diagram here, what you'll see on the right hand side here. So the stress strain diagram obtained from a torsion test is very similar to that we obtained from an actual tension test. If you go back to what we looked at in last week's lecture, when we plotted direct stress against direct strain, you had a very, very similar diagram. We had a straight portion to the diagram and then it tailed off towards ultimate failure. So it's very similar to the diagram we obtained from a material tensile test we looked at previously. The thing that is different about the stress shear strain diagram is that the yield strengths in shear and the ultimate shear strengths are a lot less than what they would be in tension. And typically, this is a sort of a crude estimate, but typically for a given material, the shear strength is about half of the tension strength, so about 0.5 to 0.6 of the tension value. So say, for example, we're considering a structural steel that has a tensile yield of around 270 newtons per millimeter squared. It could be conservatively assumed For the same material, the yield shear stress is around half of that, so around 135 newtons per millimeter squared. And that's a conservative estimate, but that's a reasonable estimate. But as with the normal stresses and the normal strains, we do see an initial proportion of the shear and stress strain diagram that has a straight line, as we saw in the previous slide here. We've got this straight line portion. You still see that characteristic, and that's basically what equals the shear modulus value. So for the shear and stresses that do not exceed the proportional limit in shear, we can state, as for any homogeneous isotropic material, that the shear stress is proportional to the shear strain, a linear relationship, and that linear relationship is due to the gradient of the line here. And this gradient of this line takes 2 points on this line and worked out the gradient of that line. So that gradient there, so my change in my y divided by change in my x kind of thing, that gradient would be the g value, we call it. The gradient is the g value. So Hooke's law does apply whether you're in direct stress, an axial tension stress, or you're in a shear stress, a torsion type test. The Hooke's law is assumed to apply in both cases, which is quite useful. So the constant of proportionality, the g term in the previous equation, is called the modulus of rigidity, or the elastic shear modulus. So g is equal to shear stress divided by shear strain. It's totally analogous to the E, which is direct stress divided by direct strain we looked at last week, but the symbols are different. So g is equal to the shear stress tau divided by the shear strain, either gamma or sometimes phi is used, as we used last week in our work, so gamma or phi. The units, again, will be newtons per meter squared, or pascals, or newtons per millimeter squared, whichever you want to use given the information in the question. So considering all planes of a cube, like we looked at previously for shear and strain, where the stress values do not exceed the proportional limit, we can have a shear strain in the xy direction is a shear stress in the xy direction divided by g, and a shear strain in the yz direction is a shear stress in the yz direction divided by g, and so it goes on. We can work out shear strains as well as shear stresses. Let's consider relationships between elastic constants E, nu, and g. With reference to the previous equations we've derived, it could be assumed that there are three distinct constants, the E, the G, or the nu, that must be determined experimentally before complex stress systems can be analysed. However, equations 19 below and 20 on the next slide, both shown without proof, indicate that only two of the three elastic constants, E, G, and nu, are required to be determined experimentally for a specific material, as the third unknown can be calculated from the stated relationships. So if, for example, Young's modulus and Poisson's ratio are known material properties, then equation 19 below can be used for calculating the shear modulus G. The equation given without proof here, G is equal to E divided by 2 multiplied by the 1 plus nu in brackets. So knowing the E and the nu, we can find the G from that relationship. Alternatively, if the shear modulus and the Poisson's ratio are known material properties, then we can use equation 20 below to determine the Young's modulus, E. In equation 20 is just a rearranged equation 19. So E is equal to 2G multiplied by, in brackets, the 1 plus nu. So exercise 9. Part A, we're asked to rearrange equation 20, shown below for convenience, to make Poisson's ratio nu the subject of the equation. So that should both the E and G values be known, this formula can be used to find the material's Poisson's ratio. And in part B, we're asked to use the equation to find Poisson's ratio for a stainless steel bar if we're given a shear modulus, that's a G value, is 75 giganewtons per meter squared, and we're given the Young's modulus, that's the E value, is 2.6 times the shear modulus value. The answer is stated here. I'll let you solve exercise 9. Exercise 9, here's the solution to part A. rearrangement of the equation for nu. Part B, calculations of nu given the information in the question. For reference, here's the bibliography used to help generate this presentation. I hope the presentation has been of use to you, and thank you for viewing.